let's recall where we are. So we wish to prove this special case of Markowitz rigidity theorem. S is SS3R, gamma is a lattice, and we are having rho from gamma to G, which is some simple complex algebraic, PG, let's say. Unknown N. You may think of it as an unknown group. It is, of course, valid in more generality. Somehow, given any non-compact other group T in S, think of it as acting on the other side, and S has a space X, considering gamma times T action on X, we may consider, given that rho, all these bi-actions, bi-representation of gamma times T on X, and this requires having some arbitrary guy L and arbitrary G times L representation, or variety, and representing X into it. T is arbitrary. In what follows, T will be, we'll consider these 6 options of T. Those unipotent group, which I remind you, commute in pairs inside S. These will be the companions of gamma. So I will change them from time to time. I will be allow myself to change the perspective. Somehow I want to see S on the other side of gamma. But I can't see S because somehow what will get me started is this availability that I will point out again in some point. The companion of gamma, in order to get started, in order to get some non-triviality of the representation theory of gamma times something on X, I would need that something to be amenable. This is why I will take T, T1, say. I want S there, S is not amenable, I will take T1. How to approach S? I will not be able to approach S. I will be able to approach T2. T2 commutes with T1. So I will replace T1 by T2 using the commutation. I will replace T2 by T3 using the commutation. I will replace T3 by T4 using the commutation. I will replace T4 using T5 using the commutation, and so on and so forth, until I will replace T5 with T6. And together, they will see all of S, right? So what comes next is indeed to explain how to use commutation. And this is related to something which I didn't use, but I did point out yesterday, that whenever I have the universal property of initial object in a category gives us not only a map from X to G mod H, but also a map from the commutation, the commutant of the acting group on X, automorphism group, the gamma automorphism group of X I think it was the S automorphism group of X in terminology of yesterday, to the G automorphism group of G mod H. Again, this was in the terminology of yesterday. I will now write a version of it in terminology of us today, but again, I will not do it in the most general form. Let me recall our specific thing. So let me now take this theorem, apply it for these TIs, and put it on the board. So fix for the gamma times. Now I'm writing something that I will do for any I, 1 to 6. An initial object and it will be X, it will be Pi to G mod Hi. Here I'm having gamma times Tix. X is S. And here I will have G coming with this initial object, some group L. This is rho times some theta I, which comes with this. And Li here is actually sum of N and I mod Hi where Ni is defined to be the normalizer in G of Hi mod. Sorry, just that. Okay, each specific subgroup T gives specific choice of initial object. Right? So we fix those. I want to initial object, let me remind you, is not canonical in some way. It is unique up to unique isomorphism. I'm making a choice here of representation. And now, observe, as we had before, that gamma times T1 times T2, we have a triply commuting action on S. Gamma act on the left on S, T1 act and T2 act on the right on S, and they do commute between themselves. So this is a very special situation. You don't see this a lot of in mathematics. And three groups commuting. Oh, maybe I should have added one more line here. We know that's a complicated word. We know this is the content of that. This is why I kept this unclean. We know that the HIs are proper subgroups of G. This is very important. We worked hard for this. Those categories are non-trivial. And this is, for this it was enough to consider the trivial representation of T1, T2. Okay. And now, let's consider not the full group T2, but one element. And let's look at Phi1. And let me note again, write too many symbols. This arrow is decorated with more symbols around it. Let me be Hassan. Let me say cheap. Okay, and now let me take T2 and think of it as an automorphism of the gamma times T1. Maybe I should emphasize difference. This is an automorphism, a grand map of the gamma times T1 space X. And let me apply again the same gate map Phi1. And that theorem, in the background of it, using weak mixing, etc., gives me the existence of this arrow. And this arrow here depends on T2. Let me use a symbol which I haven't yet. Let me call it theta prime 2 of T2 to show the dependence in T2. And check, as you did before, that theta 2 is a map from T2 to the automorphism group of this thing. So here you have an action of G times L1. And this should be equivalent with respect to this action. In particular, it is G equivalent. This will be a map into the automorphism of G mod H1 commuting with G. It will be a map into N1 mod H1. Actually, into the commutator, in a centralizer of L1 in it. But never mind that. And of course, I will denote the Zariski closure of it by L prime. following observation. That map, x to G mod H1, that very T1, when I consider x as a gamma times T2 space, and this one as G times L2 prime space, is a birep of, again, gamma times T2 acting on X. So the initial T1 object is a T2 object. And here I was using heavily commutation. Consider the category of all T2 bireps, or gamma times T2 bireps of X, and the fact and initiality in it. This is the initial object in that category. So again, T2. Oh, sorry. Oh, no. Let me. There exists such a map due to, or maybe a morphism. This is a shorthand notation for a morphism of gamma times T2 bireps. In particular, this is a morphism of this. This is a G morphism of this variety. But it has much more structure. I don't care. Again, due to this fact that this is initial in that category. Okay? Fine. But the role of 1 and 2 was symmetric, right? I didn't use any property of T1 that was not of property. I mean, I can invert the role of T1 and T2. Symmetrically, I can find a map G mod H1 to G mod H2. It would be a morphism in the gamma times T1, it would be a homomorphism. So a morphism of gamma times T2, gamma times T1 representation. Sorry. Forget this. This is a G morphism. This one and that one are G morphisms of cosine space. We get the G mod H1 and G mod H2 isomorphic G spaces. Right? This is not trivial. A minute ago, I was introducing all these initial objects. A minute ago, they were all different. But now it seems that all the phi i's are just the same map. All the hi's are just the same group. Some things are different. The li, I'm not saying they're the same. But those spaces, when I varies, are just the same space. This map, if you think about it, is the same map all over again. So, let me state this. Okay, maybe I should. It's not that G mod H2 is G mod H1. It's not that H2 is H1. It's up to a certain conjugation that they should form. Let's choose this conjugation. Let's maybe, so in that sense, maybe we change our choice here. We change the choice of H2 to be the same as the choice of H1. We conjugate things so that, without loss of generality, when we made these choices, we had all the ages are the same. All the fields are the same. write this again, because this is so important. I'm having gamma times pi. For each I, I'm having this action on X, on S, and I'm having this map, same map, phi to G mod H. The LIs are all different, but all the LIs are subset of the same N mod H. Okay, now N mod H is called active. Committing it's all these LIs are in it. And let's divide at once all the LI actions. Let's mod out this group now. Okay? Let's go to G mod N. This is the orbit space of that group action. Committing this G. G still act. Was acting on the left, still acts here. This is mod and mod H. Right? Consider this composed map here. Ti acts here on the right. T1 acts on the right. It acts here via the map into L1, which here is a trivial action. This map will be T1 invariant. It will be T2 invariant. It will be invariant under all the Ti's. So it will factor through X mod all the Ti's. Or S mod all the Ti's. What is the group generated by all the Ti's? Right? So first of all we have this, we observe that, and now this is just a point. And the image of that point will be a point in here. What will be the property of this map? This is gamma equivariant map. It will be T invariant for all the T's. But it will be gamma equivariant. This is the gamma fixed point. This is the gamma, actually gamma Zariski, rho gamma. Zariski dense. Fixed point. And what is the Zariski closure of rho gamma? Thank you. G fixed point. And what is the conclusion here? This space consists of a single point. M is G. H is normal in N, of course, and is the normalizer of H. N is normal in G. But I was insisting of, when I was discussing, of taking simple G to PG and C. At the very first, at the beginning of this hour, last hour, I was emphasizing this. G is simple. It doesn't have any normal subgroup unless there are trivial. Either H is the trivial group or H is G itself. Now, here we go. H is not G. G simple. H is not G. Implies H is the trivial group. It was trivial all along, I just didn't know it until very recently. And this map that we have here, I will rewrite it in a minute, it's actually a map from S to G, as I wanted. We are not done yet, but we are pretty close. So let me again rewrite this map under our new understanding. goes to G. This is the map phi. It's not a homomorphism of group. If it was a homomorphism of group already, I was happier. This is just a Borel map from this measured space to that Borel space. But it has a lot of equivariance property. Somehow now, I want to glue all these equivariance properties together. So far, but I know separately that it commutes with all these Li's. I mean, it's commutes with all the Ti's, but this commutation might be different from group to group. Somehow I want to glue all these Ti's generate S, the right action of S. All the Li's, now I know that the Li's are actually subgroups of G. Right? No subgroup. It was in N mod H. N is G, H is T. Somehow I want to glue together all these maps that are into one map from the group generated by the Ti's, in the group generated by the Li's, or in the global envelope of the into G. This is what is left to establish. So somehow I want to say, hey, the Ti action, I can actually see it here, and it extends into the NS action here. But I don't know that the Ti, they do act here. I don't know that they generate S in here. Right? Maybe they generate something else in here. I don't know that those homomorphism Ti do extend to a global homomorphism from S. So this is my next point. It will be slightly technical. I will use a nice trick of, instead of looking at spaces, I will look at function spaces on them once more. So this is just a trick to glue together those maps. So maybe let me just summarize some. Before doing this, let me note some fact. Look at phi of S. The image of S inside here. Somehow the way I want to think about it, phi is just it's not really a function. It's defined almost everywhere. What is well defined is the push forward of the measure class from here. Here I have a measure. I can push that measure in here. This is a measure in here. So when I write this, think of it as a measure. Take the support of that measure. This is, since everything was gamma equivariant, this is a rho gamma invariant set, closed set in here. Take the closure of the support. This will be invariant set. How many invariant sets do you have? This means now that the support is actually a risky density inside G.
I don't understand something. Like you have phi, which is an almost everywhere defined function from S into G. What is this support of phi of X? Is it a subset of G?
So this is a short-term notation. Actually, I'm having a measure here, and I'm pushing this into phi star.
Oh, right.
Mu, and if you want, this is phi star.
Okay.
Okay? But I use the symbol that I'm using. Probably I will not use this again in this course, but I'm using many times. So it's, in some sense, cases, the Lebesgue spaces I'm considering are just measures. So when for me, S is a measure now in my mind. Okay. So now the image actually, and actually it means that whatever null set you ignore here, you define phi on the rest, the image will be Zariski dense. There is no null set which is heavy enough that you can ignore it, and the image will be supported on some smaller the image will be in some strictly algebraically closed, very closed set. Okay. And now, as I said earlier, I want to consider the effect of phi on function spaces. So consider OG. What is OG? Polynomials on the affine variety G. I can pull back polynomials by recomposing with phi and think of them as functions measurable only, Lebesgue functions on S. So these are functions, measurably, almost everywhere defined functions, consider up to null set, blah, 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 complex valued on S, right? The fact that I was emphasizing here is that this is injective. I want to explain, this is a homomorphism of algebras, as usual when I apply a set map into function spaces. It's a homomorphism of algebras or abstract algebras. And if you take a polynomial, I want to show that it cannot be mapped to a non-trivial, a polynomial which is not a zero polynomial here, cannot be mapped to zero here. So it's not zero almost everywhere. The space or the set on which it is not zero is an open density. It is an open set here. It's a risky open set. And the measure sees that set. So the image is not zero. This means that this map is injective. So in my mind, I'm considering OG now as a subalgebra of LS. Don't get mad on me on doing it. If you don't like it, write the upper star here. Consider the image. But now here I'm having again here I'm having Li, G times Li active. Here I'm having gamma times Ti active. This map is equivalent, right, with respect to each rho times theta I. But now I may think of this OG considered as a subalgebra for LS is Ti invariant for all I. Do you agree? Hence, now I can glue together all the action. Hence, it is invariant and the group generated by the TIs that is S. That algebra is S invariant. And now, for the first time, I can extend the action of the action I'm having on OG to S itself. How does it disappear on my note? So I'm having that G act on the left here, and I'm having a commuting action of S by algebra, by autos of algebra. This G action came from the left multiplication by G. The S action came from the individual right multiplication by the LIs, or by the TIs. Okay, you act on an algebra, you act on a spectrum. Of course, G times S act on G itself. G acts by left multiplication. in a commuting way. I guess I need more. So let me write again. Gamma times S act here. Gamma by left multiplication. S by right multiplication. G times S act here. G by left multiplication. And S by right. I'm having this phi. And now I got a map rho times, let me denote it, theta. So I got a map as, this action, that is, I'm having a map as theta to G. The action of S on G by right multiplication is via some homomorphism into G, which is the group, this is the group of right multiplication of G. And this is for this theta. Now set, maybe this theta I should call it rho bar. And check that if we have this diagram, then rho bar restricted to gamma is rho. Okay, so we're done. Then let me review the proof now. Just so we see. The whole technical step of dealing with function spaces, etc., appearing in the end, was just a way of gluing together pieces of the covariancy we had, right? The theta i's. So once we've been here, it was just, this was the end game. We were already winning. Okay? How did we get here? To get to G, we used normality. We used that H was normal, and somehow disappears out of this discussion we had. But after setting the formalism, let me emphasize this, after setting the formalism of Barry representation, what was non-trivial here is what we did yesterday, is getting started. This was something very transcendental that we applied. This was the use of amenability. It enabled us to get started. This category is not entirely trivial. We had something going on over there. This the amenability of, say, T1 that got us started. And it was weak mixing that enabled us to prove that theorem, that we have an initial object. Then we kind of continued by successive commutation, which is some algebraic property. This is a property of higher rank group. This is why this theorem applies for higher rank groups and does not apply for rank 1 groups, or should not need to be applied for rank 1 groups. It does not apply for SL2R, for example. We've seen previously that SL2R has a free group as a lattice. It just has this free group, gamma, just has way too many homomorphisms into many things. You cannot extend them all. Maps from S to G, as rho bar here, this is something very restrictive. Lie theory studied those things. They are classified by highest weight, etc. You don't have so many. But so there is a huge difference between higher rank and rank 1, and this difference is emphasized or is manifested in this extra commutation that we have inside the higher rank groups. Okay, and now, are there any questions about this last thing?
Yes. I didn't get really how you got this theta coming from S to G. You said that S acts on the right.
Yes.
And then from
So just let me stop it now. Act on the right on G means that you have a homomorphism from S to the group of right actions on G.
yes,
And this group is G itself.
I see.
This homomorphism is theta.
Okay.
So I changed my order theta i's into, I glued them into one theta, but I didn't do it, I didn't work with these various theta i's at that point. I just observed the existence of this theta. Okay, so that was a review of that last theorem with many implications that I will not discuss now. I was, when I was preparing, I thought I will discuss arithmeticity, etc. I will not do it. Maybe I should say about the scope of the theorem. You can replace S3R by every higher rank simple group, and under some assumption called irreducibility of gamma with any higher rank semi-simple group. And you can replace G here with any algebraic group over any complete field. You don't really need algebraically closed here, but then you have to work about constructibility of morphisms. If you don't want to do it, you want just to work over algebraically closed complete fields of absolute values. If you're not C, then you need to care about local compactness. I was using compactness of projective space at some point. This is valid over C. If you're not working over C, if you're not working over local fields, you need to add something here in order to get some compactness. This can be done, but the most naive version is over the complex, and this is what we've done today. As I proved, you can replace G with every complex simple algebraic group. Same groups, same proof, just works. Okay, and now this is about this class, which was the highlight of this course, and this is where I was aiming all the time, but of course I was explaining other things as well, and I want to give some overview and to do something that I haven't done yet, and this is giving some references and some suggestions for further reading, if this is relevant for you. So, first lectures, the first day, and this was extended in the 9th. I was discussed maps from R2 to R2, which commute with the lattice. And we had a very general version of it at the 9th, yesterday, of that very thing, which I did at the very first day very explicitly, without yet discussing the things in general. So this is, this appears, the material of this appears in a paper of myself, Alex Fuhrman, Alex Ergodic, and Barak Weiss. I will not write the name because this uniquely defines the paper, but it's called Rigidity Group Actions on Homogeneous Spaces 3. And 3 because the first one, there is no one. The first one is an unpublished result of Shalom and Stiger, who proved exactly that exercise that I did in lecture 1. And they used the theory of integrability of matrix coefficients, of some unitary representations, some very, very heavy machine they had. Very complicated, and it was very restricted to that case. Later, Fuhrman came and gave another more ergodic theoretical explanation of this phenomena. And the title, as a joke, was something 2. And we understood it in a greater extent, somehow together, and we called it something 3, and published it. And I think it is quite readable. And one more thing to remark is that the abstract of this paper is made as a sonnet. So we didn't publish it in this way because we didn't want it to be rejected. So we changed the way the lines are made. I mean, it makes sense mathematically, but if you read the abstract, you should rearrange it in your mind. So this is lecture 1. Lecture 2, I was discussing generality about lattices. I was proving that SLNZ is a lattice in SLNR using this nice theorem by Minkowski, and later on, so here I was using notes by Mark Burger, which I don't know if they are online or anything. I don't know if it's published. If you want to read it, please email me and I will give it to you. I think it's course notes, and he improved much more than just that, but this very nice proof I was stealing from there, probably this is the same proof given by Ziegel, I'm not sure. Okay, having discussed lattices, and of course in lecture 1 we were relying on these results. In lecture 3 we were discussing metric action or isometric action of semi-simple groups. This was very crucial for us in our later discussion of metric ergodicity. We didn't coin that term yet at lecture 3, but this was related to how Moore thing. And I was taking in our discussion, I was using the recent notes we put on the archive with Tzachi Gelander, called equicontinuous action of semi-simple groups. So actually, of course, I was just remarking in class about equicontinuous actions, but we emphasize this in the note because it has many implications. Okay. Lecture 5. Sorry, 4. In lecture 4, we discussed metric ergodicity. So we put this result in context of metric ergodicity. So this notion appeared in my work with Alex Fuhrman. So with Alex, we have this recent note for ICM proceeding called Boundary Rigidity Representation and Lyapunov Exponents, and it appears there. It appears before in some notes that we were using. It is discussed, this notion, also discussed in the paper by Benjamin Weiss and Eli Glasner. They studied generality of metric ergodicity. And it is built on the notion of ergodicity with whatever coefficients. Is built on the study of Borger-Monod. Part of the study of bounded cohomology, they used ergodicity with unitary coefficients. And also some nice term here with respect to Poisson boundaries were studied by Kajmanovic. So all these are relevant references. If you want to study this further, lecture 5 was generality about ergodic field. So this is on the one hand is very standard and very available. On the second hand, not entirely in the form that I was presenting. So text that you classical text that you can study this kind of thing in a closest form to what I was discussing is Zimmer's book, which I already gave a reference to, Ergodic Theory and Semi-Simple Groups. And there are paper by Vardarajan and by Mackey about the structure of Lebesgue spaces, etc., 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 and compact models of Lebesgue spaces. Recently, this does not appear, so I will not write it down, but I think somehow the discussion we have is not satisfactory in the literature. Because this is so fundamental, so we can find everything in advanced paper, but not in the form that is easy to grasp. And I asked a master student of mine, Alon Lessel, he writes something, and I hope that this will be available at some point. Exactly about those things, compact models, etc., that I was presenting in class. Okay, I want to proceed fast. We are nearing the end, I think. So 6 and 7, well, this was algebraic geometry and in view into algebraic group theory. And of course, you have the classical books by Borel and Humphreys. There's also a book by Springer, but I didn't read it, so I don't know. Probably should be recommended as well. But in particular, so everything I did is here. But if you are interested in constructibility, the notion of